Notice, and this is a typical copyright. We continue with the syllabus for mathematics at the CSEC level. This syllabus became effective in May-June 2018. Normally, it will run for 10 years. However, as of December 2025, this syllabus has not been revised, but there are plans to change the structure of the exam from 2028 and onwards. And currently, there are a few pilot projects being conducted in a few Caribbean countries. The two main changes are, one, to split the exam into two parts, so you would have a part A and then a part B. And secondly, that those alternative questions from in paper 2 will no longer be available. You would have to answer all questions from all sections. As you already know, section 1, 2, and 3, all those videos have been published on YouTube in their entirety. 51 videos, so make good use of them. From these, 5 of these have been published out of 17, measurement. Next, 5 out of 18 from statistics, published on YouTube in their entirety. And from algebra, 7 out of 22 have been published in their entirety on YouTube. The others are only partially published. It did take a lot of time to set up the online school, so I have had to reschedule the last 3 parts. That is section 7, relations, functions, and graphs. This is the 4th of 26 videos, and hopefully I will finish this section by February 2026, which is this month. Section 8, geometry and trigonometry, by March 2026. And finally, section 9, vectors and matrices, by April-May 2026. Please note this disclaimer down here. This schedule is just a projection and it is not to be interpreted as a contract with anybody. From section 1, as I said, all 33 videos have been published on YouTube in their entirety, especially since this section forms the foundation on which the rest of the syllabus is based. And some of this work is even done in primary school, the upper classes in primary school, grade 5 and grade 6. Also, another reminder that you need to know the times tables from 2 to 12, especially since calculators are not allowed in paper 1. All 12 videos from section 2, consumer arithmetic, have been published on YouTube in their entirety. All 6 videos from section 3, sets, have been published on YouTube in their entirety. From section 4, measurements, some of these have been published on YouTube in their entirety. These indicated here by yellow, and the others are only partially published on YouTube. If you need to get full access to those that are only partially published on YouTube, please see directions in the description below. Section 5, statistics. These indicated in yellow here have been published on YouTube in their entirety. The others are only partially published on YouTube. Please see directions in the description below for full access to these videos that are only partially published on YouTube. Section 6, algebra. These indicated in yellow here have been published on YouTube in their entirety, especially since this is an area that most students find problems with. These others are published partially on YouTube. Again, if you need full access to these videos that are only partially published on YouTube, please see directions in the description below. Right now, we are at section 7, relations, functions, and graphs. We have 26 objectives in this section, 1 video per objective, which would give us 26 videos. Before we go on, recall I said in the introductory video that you will need a good math textbook or maybe a set of 2, especially to get more practice questions. CSEC recommends the following, shown at right here. From these, please pay close attention to these last 2, especially since they form a very good 2-volume set of math textbooks that is quite adequate for the current CSEC math exam and even the proposed changes in the CSEC math exam. This is Volume 1, Mathematics, a Complete Course with CSEC questions by Raymond Tulsi. And this is Volume 2, a picture of Volume 2. Please note this disclaimer down here. I get no financial or other benefits from the sale of these books. As of late 2024, a website with AI interactivity has been made available free of cost that deals with past CSEC math questions only. You can navigate by topics or years, where all questions for the past several years have been worked out for you. Now, if you still have a question that you need explained, you can ask the AI assistant either by text or voice, and most likely that will be explained for you. It is extremely important that you become familiar with how CSEC sets its questions for paper 2 and what will be considered good or correct answers to such questions. This is the URL for that website. The home page for that website is shown on the next slide. This is the home page for that website. You will have to register and, of course, subsequently sign in. This is the URL again up here. This URL will be in the description of this video below, so you can easily click on it and be redirected to this website. This is a reminder that you will be provided a formula sheet for the math exam for CSEC, and this is what the formula sheet looks like. There will be a link in the description below from where this formula sheet can be downloaded. Of course, if you have the full syllabus, this formula sheet is in the syllabus. This is the top part of that formula sheet, so you could see it a little closer. Please note that you do not need to memorize these formulae on this formula sheet, as I said before, this sheet will be provided during the examination. And this is the below part of that same formula sheet. While you do not need to memorize these formulae, you do need to know when and how to use them. So we are here, section 7, relations, functions, and graphs. This is a picture of what the first 5 objectives look like. Print screen, exactly from your syllabus. And then up to objective 9, print screen. Up to objective 13, print screen. Up to objective 17, print screen. Up to objective 20, again, that's the print screen. Up to objective 22, this is just so you will know where we are and where we intend to go. And finally, up to objective 26. This section has 26 videos, well, 26 objectives, and since we are doing 1 objective per video, we will end up with 26 videos. For section 7, relations, functions, and graphs. So we have finished video 1 and it is published in its entirety on YouTube. We have finished video 2 and that is only published partially on YouTube, and video 3 partially on YouTube. We are now at video 4. When this is finished, it will be published in its entirety. So we are here. Objective 4. It says use functional notation. And then explanatory notes down here, it actually says, for example, f is the function such that x maps into x squared, or f of x is equal to x squared, as well as y is equal to f of x for given domains. And then that's 1. You could count all of that as 1. And then we looked at inverse function. You count that as 2. And finally, composite functions, count that as 3. So we will be looking at those 3 functional notations. Part A, we will review or consolidate some concepts that you already met in this section so far, like these here. And then for part B, we will preview, because you didn't meet this before, 2 other concepts that we will encounter and deal with in detail later in this section: the inverse function and the composite function. We will just learn about the notation. So we are back at part A. First of all, what is a function? Now, your syllabus defines a function as a correspondence with each member of one set mapped onto member of another set. That is to say, mapped onto a member of another set. And that is from page 62. A better working definition is this: a function is defined as a relation in which each element of the domain is mapped onto one and only one element of the range from the codomain. So part A, question 1. We saw this in the last video. You have domain over here. You have a codomain over here. This is a function f such that x maps onto 4x. It is a function. 1 from the domain to 1 from the codomain. Now consider the expression below, this expression here. Now this is the standard format of expressing a function and will normally indicate the domain. For example, f is the function such that x maps to 4x. That is how you read that. F is a function such that x maps to 4x. Now don't be misled by this f here and think that that means function. It does not. It's just a way of naming a function. We could have named it g is the function such that x maps onto 4x, or b is the function such that x maps into 4x. So don't be misled by this f here. It's just a name of a function. Now with the domain shown at left, the full standard functional notation becomes this: f is a function such that x maps onto 4x, where x is a member of the subset 1, 2, 3, and 4. That is to say, f is the function such that x maps to 4x, where x is a member of the set 1, 2, 3, and 4. That's the full functional notation. Now consider this expression here. F is a function such that x maps onto 2x plus 4, where x is a member of integers from 5 to -5. This can be stated as f of x equal to, now I know we read this as f of x, but it is probably better to say f at x, because you will take that 5, for x first, and then you will take that 4 for x, and so on. So we normally say f of x. But for you to understand it a little better, maybe you could say f at x. X could be 5, x could be 4, x could be 3, x could be -4, and so on. We will still say f of x, but remember, think in your mind that f at x. So f at x is equal to 2x plus 4. And then that can also be stated as y is equal to f at x, or f of x. Now, if you combine those two, you get y is equal to 2x plus 4. So you take out all of that there and put in y is equal to. Now you see this equation here, y is equal to 2x plus 4. That is called the defining equation. And we got that from the function here, the function f, such that x maps onto 2x plus 4. This is the defining equation from that function. So if you substitute -5 in here, -5, you will get -6. That will be the range. Well, that will be the image in the range. If you substitute -4, you will get -4. If you substitute 0 in this equation, you will get 4, and so on. So this is why I am saying it may be better for us to say f at x, but I know what we normally say is f of x. And so what you have here is a domain, and what you have here is the range. If you were to plot that on a graph, this is what the graph looks like. We do have the relation down here, which is a function. So from f is a function such that x maps onto 2x plus 4, and we are using these as individual members of x. We get y is equal to 2x plus 4, and when we substitute 5 and 4 and 3 and so for x, we get these numbers here. We plot them on a graph, and we get this graph over here. We can use the vertical line test, and as you can see, if we use a vertical line from anywhere on this x-axis, it will touch that graph at only one point. You come across here, and you get only one value at the y-axis, any vertical line. So this relation has passed the vertical line test, so it is a function. We will consider 2 more graphs like this before we move on to part B. If you find this video useful and interesting, please like and share. That is to say, like and share. You may also consider subscribing to this channel. We are looking at another example. Consider the expression below. F is the function such that x maps onto x squared minus 3, where x is a member of the integers 4 to -4. Now this can also be stated as f of x equal. So what this really means is that we will take these numbers here and place them in that x one at a time and see what we get out. So it is really f at x, f at 4, f at 3, f at 2. But that's not what we say. We say f of x. And this can also be stated as y is equal to f of x. And of course, these are the values of x that we will use one at a time. Therefore, we can now say y is equal to x squared minus 3, and we will be using these as the values for the domain, for the x values. Now, this equation here, y is equal to x squared minus 3, that is called the defining equation from this function up here. So now, if we substitute these numbers one at a time, let's begin with -4. Well, you could begin with 4, which means we start down here, and then the y value, which would be the range value, would be 13, and then you go down the line, or you go up the line. If you substitute 0 for x, you get -3 because that will work out to be 0. So you get -3 and so on. Let's do a vertical line test on this. So remember, from this function, with these values as domain, we get this equation. We are still using these values as domain, and using those values as domain, we get these as the range. That is to say, if you substitute 4, well, let's say you substitute -3, you are going to get 6 as the image, which is part of the range. So the vertical line test, you draw a vertical line at any point here, and you will notice that it touches the graph at only one point. You come across here and you get the y value. So it has passed the vertical line test. In this case, it's a many to 1, because you could get at 2 here, you could get that value, and at -2 here, you could get the same value. However, each domain value has one range value. Now consider this expression below. Remember, we are learning to use functional notation, and we are looking at this part up here, all three of them together. The function f is such that x maps onto 3x squared plus 2, where x is a member of this set, 4, 3, 2, down to -4. Now, this can also be stated as f of x. Remember, we now have this equal sign here, which means we are going to deal with each of these here as x individually. So as I said, think of this as f at x, f at 4, or f at 3, or f at -4. But we normally say f of x. And this can also be stated as y is equal to f of x, which means that y is equal to 3x plus 2. And we are using these here as the domain. This equation here is called the defining equation from this function up here. If you work that out with the various x values, for example, f at 1, when x is 1, you will get 5, and so on. So these would be the domain elements. These would be the range element. Let's plot a graph with that. Y is equal to 3x squared plus 2. So from this function here, f is the function such that x maps into 3x squared plus 2 for these x values. Then we get this equation, y is equal to 3x plus 2. So this is a defining equation from that function up there. We can use a vertical line test, and you will notice that any vertical line here will touch that graph at only one point, which would give only one y value or one range value. So now we move on to part B. We are finished with that part up there. We will now look at inverse function and composite function. And to do that, we will do a preview of these two concepts that we will encounter and deal with in detail later in this section. Inverse function and composite function, because you haven't done this before. For obvious reasons, these will be a little more difficult for you to understand now, but not to worry. This is just a preview or introduction to the notation of these two concepts. Later on in this section, objectives 16 and 18 to be specific, we will deal with them in detail. Now, so objective 17 says, state the relationship between function and its inverse. Now, an inverse function, written like that, is a function that undoes the original function, f of x, meaning that if f of x is y, then inverse f of y is equal to x, essentially swapping inputs and outputs. To find the inverse, replace f of x with y, swap x and y, and solve for y. I will do this, but at this time you are not required to know this. But I have to do this for you to understand how to use inverse function notation. Now notice, do not confuse inverse f of x with 1 over f of x. And secondly, the domain of f becomes the range of inverse f of x. We will briefly consider two examples of this as your introduction to the notation of inverse function. Example 1. Consider the function f such that x maps onto 2x minus 6. Now state inverse f of x. Okay, I will do it. You don't have to learn this at this time, but I will do it so you would become familiar with it. So to state inverse f of x, we have to do 4 things. First, we will replace f of x with y, so that f of x now becomes y. The rest remains the same. Secondly, we will exchange x and y. Where you have x, we'll put y, and where you have y, we'll put x. So that y becomes x, and this x becomes y. Thirdly, we will make y the subject of the formula. So we rearrange this equation to make y the subject. And to do that, we get y is equal to this. Finally, we replace y with the inverse function notation of x. So we replace this y with inverse f of x. We get this. Note, in this objective 7.4, you are not required to actually find the inverse function, just to use its notation. I don't know how you are going to use its notation if you don't at least see what inverse function means. In objective 17 and 18, we will actually have to find the inverse of the function. So this is a preview. That's example 1. Let's look at example 2. Consider the function, this function here. Find the inverse function of x. We want to find inverse function, and this is the function we are given. Replace f of x with y, f of x with y. So y becomes whatever else is here. Secondly, exchange the positions of x and y. So that y now becomes x, and this x now becomes y. Thirdly, make y the subject of the formula. So we rearrange that equation there and make y the subject of the equation. And y is equal to 4x minus 8. And finally, we replace y with the inverse function notation of x. So we replace this y with inverse f of x is equal to 4x minus 8. As I said, in this objective, objective 4, you are not required to actually find the inverse function, just to use its notation. But I said, how are you going to use its notation if you don't know what it is and how it can be found? In objectives 17 and 18, we will actually have to find the inverse function. So we finish with inverse function. Now we are going to deal with composite function. And it says that f g is equal to f of g of x. For obvious reasons, these will be a little more difficult for you to understand now But not to worry, this is just a preview or introduction to the notation of these two concepts. Later on in this section, objective 16 and 18, we will deal with them in detail. So derive the composition of functions. That is actually objective 16 later on in this section. And it says composite function of no more than two functions, for example, fg or f squared given f and g. So we just did this. You read that as f is the function such that x maps onto x plus 4. Now what that means is, let us say we have a functioning machine, excuse the pun, we have a processing machine that performs function. This is the machine. You input these values 1, 2, 3, 4, 5, and 6 for x. Now what the machine will do, it will add 4 and spit out the results on the right. So you will get 1 plus 4 would give us 5, and so on. Now this, of course, is a domain, and this over here is a range. But you may also have g is the function such that x maps onto 2x minus 3. And you could do the same thing here, 2x minus 3. But what is f g or f of g? Now remember this, you read that as f is a function, or actually f is the function, such that x maps to x plus 4. G is the function such that x maps to 2x minus 3. So you have two functions. What is f of g? That brings us to the concept of composite functions. Now fg is not f multiplied by g. Think of it as a new function, f of g, like that, or like this. Unfortunately for us, CSEC just write fg, like this. But it also tells us that that means f of g of x. So composition of function combines two or more functions like f of x and f of g by plugging in the output of the second function into the first, creating a new function often written as f on g or f of g or f circle g of x, or f of g of x, meaning f of g of x, where the output of g of x becomes the input of f of x. So you have a chain. You have input of x becomes the output of g of x, which becomes the final output f of g of x. And we will consider this as we go along. The order matters. F of g of x is not the same as g of f of x. Note in this objective, you are not required to actually find the composite function, just to use its notation. But I have to show you what it is so you could understand what the notation means. So let us say you have those. F is a function such that x and g is a function such that x. What is f g? As I said, unfortunately, CSEC uses fg, but it also tells us that fg means f of g of x. Now, f of g of x means you apply function g first and then apply the function f to the result, essentially calculating f of g of x. It's a composite function where the output of the inner function, which is g of x, becomes the input for the outer function f. So as I said, unfortunately, CSEC uses this, but then tells us that it means f of g of x. So okay, example 1. So we have this function here, and we have this one here. Determine fg, or f of g of x. F of g of x. So what you would do, you would substitute g of x for x in f of x. So see where this x is? You will substitute this g of x. That's all there is to it. So the function f is this, the function g is that. Now we want f of g of x. So we will take this function here, and where x is, we will replace it with this. So now we have f of g of x is equal to f of x, which is equal to this. Now remember, that is replacing this x up here with this x down here. And so you get that. So this is the composite function notation, fg. And you can simplify this, and you get f of g of x, or fg, is equal to 2x plus 1. Again, you don't need to know how to actually calculate the composite function. Just be aware that there is something called f of g of x. Let's reverse that process. Now, previously, we just did f of g of x, or fg. Now we are going to do gf, which is g of f of x. Now, f of x becomes the input. So you are going to substitute f of x in g of x. That is to say, wherever you have x here, you will put in all of that. So this x here, we will replace it with that. So you get g of f of x is equal to gx, and now you maintain that 2, you maintain that minus 3, and all you do is substitute for that x what you have up there. So 2 times x plus 4 minus 3, which is gf, or better still, g of f of x, which is 2x plus 1 when you simplify this. Again, you don't need to actually know how to find the composite function in this objective, but as I said, you need to be aware of what the notation is for composite function. We will look at one more example. Let us say you have the function p is such that x maps onto 3x minus 2, and the function v where x maps onto 2x plus 3. Determine pv. So that will be the function p of v of x. So the function p of v of x. So now we are going to substitute v of x in p. So in other words, p is the main function, and where this x is, we will substitute this part of v. So we rewrite p v. Now this here is still p, that there is still p, but where x is, we will take it out and put it this part here. So you get 3 times 2x plus 3 minus 2. And you simplify that, and you get p of v of x is equal to 6x plus 7. As I said, you don't need to know how to find composite function in this objective. That's for a later objective. And let's reverse that. Just now we were finding p, v. Now we want to determine v, p. So now v is the main relationship, and we will substitute the p value for x. So now we're finding v of p of x, v of p of x. So you substitute p of x in v of x. So this is v of x. You still have that 2, you still have that plus 3, but you take out this x and you put in 3x minus 2. So you have v of p of x. You are substituting p of x in v, and you get this. So by now, I hope you become a little familiar with this fg, or f of g of x, which represents a composite function. And that should suffice for this objective as an introduction to functional notation. So objective 4 in section 7, use functional notation. These are the examples we have to consider. First of all, we looked at this first one here. We count all of that as 1. Secondly, we looked at inverse function. And thirdly, we considered composite function, which has this notation, or this somewhat confusing notation. And that brings us to the end of video 4 based on objective 4 in section 7. This is an overview of how the videos of this section will be published. As you could see, this is video 4, and it will be published in its entirety.